2 years ago, this thing had a couple of trees growing right about here. By the end of this video, it's going to move under its own power, electrical power. But before we get into that, we'll do a little history lesson. I got this book from an auction. It was in a box with a bunch of other ephemera and some micrometers. Mechanical Engineer's Handbook, Lionel Marks, first edition, fourth impression, from 1916. It's unfortunately in really bad shape, but if we turn to page 1203, we hit the section on electric vehicles. It's actually some pretty neat reading from a historical standpoint. The section we care about for this video is motors. 1916 state-of-the-art was series wound motors. Series wound motors have very good starting torque. That's why they were using them then. 2 to 2.5 kilowatt rating, generally used for pleasure cars. And since we're talking about motor control, basically it was 5 or 6 discrete forward speeds. The field coils are generally arranged so they can all be connected in series or in 2 parallel groups. And then it would also have a resistor, so you could do combinations of series or parallel with or without resistor to get different speeds. Lots changed since then. Fast forward 99 years and you get the 2015 smart car motor that now lives in my Jeep. This is a 3-phase permanent magnet alternating current motor. If you're around workshop tools, you're probably at least aware of 3-phase motors like the one on my milling machine. Despite the size and weight of this thing, it's actually only a 0.5 horsepower motor. There's no date on it, but I would guess this is probably the original to the milling machine, so 1947. I don't have 3-phase power coming into my shop, so I'm using this variable frequency drive to drive the motor. It actually turns single-phase AC into direct current, and then into 3-phase power. And if we change the frequency that the drive is outputting, the speed of the motor changes. And so that's basically how we're going to control this thing. We just need a variable frequency drive, or what in an EV is called an inverter, to put 3-phase power into the orange connector there. This one is an induction motor. It has a metal rotor, but the rotor isn't actually magnetic. The magnetic field in the rotor is induced by the rotor rotating through the magnetic fields of the windings. I try not to think about it too hard because it makes my brain hurt. In this motor, the rotor actually is magnetic. That's why it's called a permanent magnet motor. And we need to know the position of those magnets, but we'll get to that one later. Enter the second generation Toyota Prius inverter converter. This one is actually 3 inverters. The Prius had 2 motors, and there's also one for the air conditioner. We're only going to use one of them. These things are great because they're readily available, fairly cheap, and the guys that have been hacking these and testing them found that they're really pretty robust. If you put too many volts or too many amps into it, it basically just kind of laughs at you and turns itself off, which is good for this sort of shenanigans. I got this one off eBay, and it only came with 2 bolts on the lid, so someone's already been in here. And I did already check to make sure that these capacitors are discharged. One of the kind of neat things about this is really only the power electronics stage of it. All of the logic comes in through this connector, so we just need to put some signals in here that tell this what to do. Luckily for me, it's already been done. This is the Openinverter Project Gen 2 Prius control board. It comes as this kit from openinverter.org. Johannes Hubner is the guy's name. He has a YouTube channel that if you want to know more about all of the inner workings of this and all the work that they've been up to, check that out. You should also check out Damien McGuire's channel. He does a lot of this sort of inverter hacking too. They've also got some really good videos on how to actually set these things up. I'm going to try not to recreate that here because they know what they're doing and I don't. But I figured this is a good opportunity to show the process from the perspective of someone that's never done it before. The first step on this is to solder on the connectors. I think it's really a production issue on these boards, so Johannes doesn't have to solder them all. But it kind of feels like that thing with cake mix where they figured out people liked it better if you had to at least crack an egg. Feels like I'm doing something with electronics here. Soldering electronics like this is not something that I've done a whole lot of, but it's really not too bad. Like the saying goes, don't be scared to try it. I say that and that one's ugly. It's not perfect, but that wasn't too bad. So, that's a little Wi-Fi module. The next step is to feed 12 volts into this thing. And hopefully we'll start seeing things blink. Things are blinking! It's alive! It even says right by that LED, alive. All of the inverter management is via an integrated web page on the inverter control board, so it's just a matter of connecting to the built-in Wi-Fi network on it. And we're in. And I think this can go in the box now. Kind of a smart setup on this. One plug basically goes to the vehicle, and the other plug is for all of the connections to the inverter. So I'm just making up a wiring harness for that. Starting to get the hang of these things, but I will say, crimping ain't easy. Satisfying click number 1. Satisfying click number 2. Not satisfying. Why not satisfying? Satisfying click number 2. So really this process is just a lot of testing at each stage, verifying everything is working before moving on to the next stage. Let me try to explain this rat's nest. This power supply is supplying the controller and 12 volts into the inverter. This battery is hooked up through a 55 watt light bulb and a fuse to the high voltage side of the inverter. And because it's a complicated system, the reason that there's so much testing along the way is so if you make a mistake, you can catch it early, like if you had 3 of your wires in your connector 1 pin off. Not that I would do something like that and then chase my tail for a long time. But finally, I have 3-phase blinking lights. It's kind of hard to see what's going on here, but I have these in a delta configuration and running at 1 hertz, so... Well, finally passed that test. Except it's supposed to look like that. So I thought what I was seeing was just the light bulbs weren't lighting up evenly because I just grabbed 3 random light bulbs and they were different. But it turns out I made some mistakes, and I spent a long time fighting that. So a lot of what I'm about to say is wrong, but I'm going to leave a lot of that in because I think it does speak to sort of the troubleshooting process and sort of the process of getting something like this going. So the next step is to put the inverter in the Jeep. I made a very rough, cardboard aided design model of my battery box. I've got the inverter just sort of slung with some cam straps for right now, but it kind of turns out that this is where it goes. I sort of want it as high as I can against the hood, and then obviously as tight to the firewall as I can reasonably get it. Since my motor leads are coming out here and then going down that way, this is sort of the best orientation for having this in here. If I turn it 90 degrees this way, they would try to go back underneath it, which I don't think I like as much. I don't think I want to permanently mount that until I have the real battery box in here, because it might make sense to mount the inverter to the battery box. But having it hanging here for now should at least let me get the lengths of my cables worked out. I'm using 1/0 or 50mm squared shielded cable for this. Orange insulation, because that's standard for high voltage in electric vehicles. They all have it. It's sort of a safety thing. If you see an orange wire, you know you probably shouldn't chew on it. It took me a minute to figure out how this connector goes together. This little threaded terminal gets crimped on the end of the inner part of the wire. Then it gets one of these pieces, and then one of those pieces, and those snap together. And then it gets one of these pieces, and one of those pieces, and those snap together. And then that little piece gets crimped on to the shielding. And then that whole thing goes in here, snaps in there, gets one of these. Turns out a 13mm socket, 12-point socket kind of fits on there. And then gets one of these. And then the little sealy bit. And the little snappy bit. And I found some more parts that look like they ought to go in here. Get it right around the end there, right here. Yeah, you can stop it. So I've set up here my official Openinverter style test rig. I have 3 battery modules charged to about 40 volts each in series for a total of 120 volts. These battery modules do have a built-in BMS, but putting them in series like this isn't a great idea because if the BMS fails, it tends to fail open. That runs down to a fuse, and then through this 100-watt incandescent light bulb. The light bulb does a couple of things. One is it will give us a visual representation if all of a sudden we're drawing a lot more amps than we should be. The other thing that's neat about incandescent light bulbs is they're very low resistance when they're cold, but as they light up, the resistance goes up, so it's sort of self-limiting. What this is going to do is serve as a pre-charge resistor. The inverter has a massive bank of capacitors on the top, and when you first put power to it, there's going to be a rapid surge of current to that. And when that happens, you want a resistor in the circuit to limit the inrush current. Similarly, the light bulb's also going to serve to limit any fault currents if something goes wrong. Next we have a switch that's wired in parallel with the light bulb. So once we're confident that things are working the way we can and we're pre-charged, we can turn that switch on and essentially bypass the light bulb. And the last one is I have a switch so that I can turn on and off the high voltage system. Now I think it's also important to say that none of this is really wired right. This is all test setup and will get replaced with proper contactors and pre-charge resistors and all of that once everything is working and we're making it permanent. Test purposes only. So we'll turn on this switch. We should see the light bulb light up while it's pre-charging and then go out. That is off, so that is not bypassed. That wasn't much. And we can see on the web interface UDC, which is our DC voltage, is now 122.68 volts, right where it should be. So we're going to start feeding some current to the inverter, and with one wheel jacked up, open differential, we should see this wheel start to spin. So we're going to go 10%. We can hear the inverter whining a little bit. Let's go to 15%, 20, 25. It's trying to move. Not doing a very good job. So that didn't work. And it took me a while to figure out why that didn't work. But basically, even with this thing in reverse, low range in the transfer case, spinning that motor in open loop mode doesn't have enough torque to even make the drivetrain move. Allow me to vastly oversimplify how this motor is working. Around the outside we have a bunch of coils of wire, and in the middle we have a permanent magnet rotor that spins around, something like that. And so what we're doing is we're just pumping alternating current through these coils, kind of all willy-nilly, randomly, and asking this rotor to spin around. Ideally, we have the magnetic field of our windings closely coordinated with the position of the rotor. And so ultimately the solution to this is to wire up the resolver so that we can coordinate our magnetic fields with our rotor. But we're still in the test phase. We're working through one step at a time, checking to make sure everything is working right. So that would be kind of getting ahead of things. But sometimes I'm bad at planning ahead on things and didn't realize that I couldn't pick up 1/0 gauge cable lugs just off the shelf locally, so I had to wait a few days for those, and in that time, I did wire up the resolver. The resolver has 6 wires going to it, so 3 pairs. One pair is the exciter, and you can figure out that one by testing the resistance of the pairs when this is actually hooked into the motor, but since that's underneath the Jeep, it's a lot easier for me to show it to you here. Anyway, this one has lower resistance, so that's the exciter, and then these are the 2, I guess, outputs. The problem is figuring out which combination of these is positive and negative. And so this is just sort of one where you have to kind of hook it up, try a combination, see if it works, and I guess kind of brute force it. In order to test the resolver, I need to rotate the motor, but since I've already got it hooked up to the drivetrain, I've just got one wheel jacked up. Since I'm running an open differential, if I spin one wheel, it'll spin the motor. I've got it in reverse right now so that it will spin the motor basically as fast as I can by spinning this. And then I'm just plotting the resolver position as I spin the wheel. Basically what we see is a pretty ugly looking plot, but it's going from 360 down to 0, back up to 360, down again, and it keeps doing that. So somehow I got that right on the first try. It's always better to be lucky than good. Someone's going to get triggered by me using white zip ties and cutting them off like this. even though this is all just temporary. So now back to the problem at hand. If we take the transmission out of gear, start our inverter in manual mode, give it 20% amp nom, and then go down and plot our angle, what we see is the motor is in fact spinning now. But our light bulb is flashing, which means we have a problem. So I kind of chased things down a bit. I was getting a desaturation error as well. And what that led me to do was to do the test to see if any of the IGBTs were blown on this. So if we have the multimeter in diode mode and put it onto the DC bus here, we should see this climb up to 2 volts and then say open circuit, which is what we're getting. And then if we swap the leads, we should see it start negative, climb back up, and hit about 0.6 volts. We're only getting up to about 0.4 volts. If it was 0.3 volts, that would be a clear sign that we have a failed IGBT. So I'm thinking, putting the pieces together here, I've got a bad inverter. So I picked up another inverter, and well, immediately this one looks much less like it's been at the bottom of the ocean. It's a lot closer to what it's supposed to do. I got this inverter hooked up, and it did exactly the same thing. So I went back and checked for the 3rd time my wiring, and it turns out I did have one of the connectors pinned wrong. But now, we have 3-phase blinking lights properly. Well, let's see if we got anything happening. Trying, go up a little. It's trying to do something. This took some fiddling around. Basically, I had to turn off the resolver. I just set the resolver parameter to single, and now 10% amp nom. So that's cool. Now we can move on. I have flashed on the FOC firmware, which will let me use the resolver to control the motor. I had to do a little bit more tweaking and tuning of parameters. One change from Damien and Johannes's video is that now you use the manual start function rather than manual run mode, which means I had to calibrate my throttle in order to get it to start. It thought the throttle was pressed and wouldn't let me start. So I figured that one out. I also figured out I had to change my pin swap, which is getting way off into the weeds, but I found a parameter file on the Openinverter forum for someone that was running this motor with this inverter, and they used pin swap 7. But now I can put a little bit of current in here and make the wheel spin that way. So now I need to go through and figure out the position of the resolver relative to the position of the magnets on the rotor. So this is basically just sort of a brute force, changing this by 1,000 points, see if it runs, and keep repeating that process until you hone in on where the actual offset is. Just so I could see easier, I pulled the transmission cover and shift tower off, and so far I've only shot gear oil out of it once. So I've got this to the point where even if I pump 120 amps of D current in there, it twitches but doesn't spin. So what we're doing is we're working through smaller and smaller intervals, getting this to the point where the pole of the magnet is lined up with the pole of the coils. As you get closer, you'll see the thing twitch back and forth because there's not enough offset to actually make it spin. And as you home in on it even more, you'll see less and less twitching. I'm just going to try to get this as close as I can. So I've got this to the point where we're just kind of seeing a little bit of twitching and rattling, which is good. And with a very small amount of D and Q current running through it, I can get it to move. Throttle pedal works. And if I put it in reverse, it spins the other way. So I think we're ready to button this thing up and take it for a test drive.
Couldn't figure out why the thing was making noise, but not actually moving. Turns out I still had it on the jack.
The tunnel of trees!
Overall thoughts on the Openinverter system? I think what makes it extremely versatile and powerful is also what makes it a little bit tricky to set up if you're not familiar with it. I think one of the common problems with an open source project is the person that made the system and actually knows how it works isn't always the one that writes the documentation for it, and the documentation doesn't always evolve quite as fast as the rest of the system does. But I muddled my way through it, and now the Jeep moves under its own power. My goal was to get this thing moving by the end of summer, and since it's not even the end of July, I'll call this one a success. I should move over a little bit. Obviously, I've got a whole lot more tuning to do on this, and I need to make all of this stuff permanent. Before I do that, I'm going to have to get the batteries in here. That's a process that's going to take some time, so it might be a while before you see another Jeep video. I've also got a bunch of other projects I want to catch up on. So hopefully you want to see some of that, and if you do, stick around.